open data in a way. So it's just repackaging StatsCan data in a more convenient way. But I'm not sort of actively involved with the community at this point, except really pushing for open analysis, which means sharing the code for analysis for increased transparency, reproducibility, but also adaptability. So you can kind of take what somebody else has done, build on it, improve it.
Yeah, no, that's good.
And you sort of slowly get to something better instead of,
yeah. You taught at the university, you taught mathematics. Can you explain what your background is there? Oh,
yeah. So, well, I did get, I guess I did an undergraduate in physics and computer science, and then I did some graduate program in physics, went over to mathematics, got a PhD in mathematics, and then did a couple of postdocs and things like this, and taught, did research. And then at some point sort of sidetracked and started my own company. First building a product for daycares in Taiwan. It's kind of random, but sort of a software as a service type thing. And then started slipping into data analysis, more data science type of things. Suited my math background a little better, found it interesting and challenging. And so did that mostly using open data, Canadian data. Started out really with CensusMapper, which was more of a project just to make StatsCan data more accessible to everyday people. And then went into doing analysis with Canadian data. And yeah, that's where I'm now.
Yeah. So you're going to show me, and I'm going to be able to do the takeaway today is I will be able to apply the CensusMapper API to Coburg, where I live. And then I can turn around and show others how to use it as well for their communities.
Right. So we'll start out maybe just by looking at CensusMapper and just how to make a map, how to explore StatsCan data around where you live or anywhere in Canada, really. And then from there, maybe how to build on that and start to do a little bit of just fairly basic at this point analysis as a starting point of how to maps are great for exploring things, but maps aren't analysis. So we'll just try to make that next step to actually use it to generate more insight and understanding.
Yeah, and Jens, before we start, I've been following a lot of this big data machine learning, and it's of course in the press, it's a news item seller. Could you comment just briefly with your background in mathematics on how data science is affecting traditional statistics?
So there's a lot of talk about data science, big data. It's not really always clear what the boundaries are between sort of traditional statistics and modern data science. In the world where I'm in, things are still generally small. In CensusMapper, we have maybe a couple billion fields of data. And so I would consider that small. All the analysis I do, most of it runs on my laptop. Very rarely will I go and get some cloud compute just to speed things up a bit. It does happen, but mostly it's in the realm of sort of maybe medium-sized data. It won't fit into Excel, but it really doesn't need anything big. Machine learning is a powerful tool, very easy to use, that can help with analysis, although in most cases, classical statistical methods work just as well. At least in the world where I'm in, I tend to be conservative. If something traditional works almost as good as machine learning, I'll stick with more traditional methods just because I feel I understand them better. I can explain them better, most importantly. But there are instances where machine learning has adds a lot of advantage to classical methods, especially if I look at predicting things and where I will employ it.
No, that's good. And I think your comment about it's easy to use some of the machine learning algorithms that are in the cloud now. And one of the things we've seen with the COVID is the The data modelers will say one thing, and then as they're using real-time or near real-time data, their model changes, the predictability of their model changes, and then they have to revise it. But in the meantime, the politicians have sort of made decisions around what the data scientists said they should be doing at this point. And then when more data comes in, that changes. The example was, at the beginning of the COVID, it wasn't advised to wear, it wasn't necessary to wear face masks. And then of course now it is. Do you want to comment briefly on where we move
COVID
into?
Sure. COVID is an interesting field. So there are many things coming together. Well, one thing on the data side is we have a lag between new cases showing up after testing, and sort of from infections to a new case showing up in a test. So what that means is we're always behind in terms of data. So what we're seeing today in terms of the case numbers coming up, it's infections maybe 5 days ago that happened. Maybe 7 days ago. It really depends on jurisdiction to jurisdiction, how good they are of getting people to come in and test as soon as they have symptoms, and then how fast they are in turning around the tests. So that's a challenge that whenever we try to make decisions today, we won't see the impact. We won't start to see the impact a week from today, and probably the full impact won't be visible until 2 or even more, 2 weeks or even longer. In terms of the science behind it, COVID is new. So there are some things that we didn't know quite well at the beginning, and there are other things where maybe we hadn't been paying enough attention to just generally how flu or other respiratory viruses work. Masks is a good example for that, where we just were really late in recognizing that this may be an important part of our strategy. And that's more a science thing than a data thing.
Yes, yes. But I guess, the science underlying all modern natural science is the mathematical language that is common across the sciences. I'm thinking of, Descartes and the
yeah, and there's also
analytical geometry, for example.
And there's also, I think, the question on how do we deal with uncertainty? Traditionally in science, we sort of hold on to our prior beliefs until we have overwhelming evidence that we were wrong, and then we adapt. That's a typical pattern of science. Science is conservative that way, to adopt new knowledge. It takes overwhelming evidence to overturn what we thought was true before. But in a healthcare situation, that's not necessarily the best strategy. There, we should probably apply more the precautionary principle that tells us that unless we are sure that, say, the virus doesn't spread through aerosols, maybe we should employ protections against aerosol spread. But we kind of acted the other way around. We kind of assumed it's mostly a droplet-based transmission, and we kind of ignored the aerosol side of things a long time without having evidence that we can ignore it. We didn't have evidence that it is aerosol-based that was very strong at the beginning. But I think the precautionary principle would have been a better choice from the beginning, rather than the sort of science conservative thing where we wanted the overwhelming evidence before we acted.
Right, not very good point. And on that, we'll move into our hands-on workshop.
All right.